The figure below shows the graph of f prime. That's really key here. This is the graph of f prime. It's also mentioned right here. And then it tells us a little bit more information about its horizontal tangents and vertical tangents, which is fine. Based on the graph, find all the values of x from -7 to 7 at which f attains a relative minimum. This right here, given f prime, we can say already f attains a local min at x equals blank because f prime changes from, now if it's relative minimum, f prime changes from negative to positive. So if here's f prime, where do I have the graph changing from a negative value to a positive value? Only a -1. That's 2 points, one for the correct value of x, and then one for the justification. By that exact same logic, I can clearly say, if I want to find the locations of all relative maxima, I can use the same logic, except that a couple things change. I'm no longer changing from negative to positive, I'm changing from positive to negative. And if I want to find out where f attains a local minimum, I got to find that positive to negative shift, which occurs at -5. Same thing for the 2 points. According to the graph, find all values of x from -7 to 7 at which f double prime is less than 0. What's the connection between f double prime and f prime? When f double prime is less than 0, f prime is decreasing. So let's look at this graph and figure out where is this graph decreasing. Here? Here. So the answer would be from -7 to -3, union 2 to 5. 1 point there. For the interval from 0 to 7, explain what x value, the absolute maximum of f, would occur. Justify your answer. If we look at just the graph from 0 to 7, the one thing that does stand out is that f prime is positive. If f prime is positive, that directly leads us to be able to say f is increasing. So if f is increasing from 0 to 7, that means wherever the graph is, it's constantly going up. Therefore, its highest point will be at 7. So that's all we need to say here. At x equals 7, because f prime is positive for the interval from 0 to 7. And that's it. We've identified where it occurs, and we have a justification for backing up why it's true. Lastly, let g of x equal sine squared of x minus cosine of x. Find all global extrema. Open interval, sine chart. Finding the derivative. 2 sine of x times cosine of x. I'm using chain rule. This is the same thing as sine of x quantity squared. Derivative of negative cosine is positive sine of x. In order to find the critical points, we set this equal to 0. So that means we factor out a sine of x, and we're left with 2 cosine of x plus 1. When does sine equal 0? At x equals 0 and x equals pi. Both not included in the interval. When does cosine of x equal -1/2? At x equals 2 pi over 3 and 4 pi over 3. 4 pi over 3 is not in the interval. So we only have one critical point, and we're going to put that on our sign chart from 0 to pi. We put down 2 pi over 3. Plug in a number smaller than 2 pi over 3, pi over 2, into the derivative. If you plug in pi over 2, you get 1 times 1 positive. Therefore, must be G must be increasing. From 2 pi over 3 to pi, pick a number, plug it in, you get negative. Therefore, we notice we have an absolute extrema at 2 pi over 3, and that absolute extrema is a maximum. So, since G prime is positive for the interval 0 to 2 pi over 3, and G prime is less than 0 for the interval 2 pi over 3 to not infinity, but rather pi, there exists a global min at x equals 2 pi over 3. If you want to know the points here, we have 2, 4, 6, 7. We only have 2 points here. The 1 point comes from taking the derivative setting equal to 0 and your justification.